Here we go. Oh no, I don't think that shows. Let's see here. I decided to read the scripture that's on my door. So for some reason they put sticky notes everywhere with scripture. Right? It's some kind of probably it's a Caesar project. Who knows? I don't know. It's some kind of project. I will say I think that's a little more legitimate Caesar project than, like, I don't know, being like something crazy, like being a bodyguard for a mascot. Like, is that a thing? Like, that's just crazy.
They probably start evangelism.
Yeah. Anyway, they put Titus 3:14 outside my door, so I'll read like maybe the verse before it. Diligently help Zenas the lawyer and Apollos on their way, so that nothing's lacking for them. Our people must also learn to engage in good deeds to meet pressing needs, so that they will not be unfruitful. All who are with me greet you. Greet to those who love us in the faith. Grace be with you all. This is the end of Titus chapter 3. So, to summarize, get a job, be productive, help people. I think it's probably good advice, right? But I mean, it's scripture. I guess I'm not allowed to say otherwise, right? So, you heretic? No. Try to minimize the heresy in here today. But let me begin with a word of prayer. Dear Father, we thank you for this day. I thank you for this class, for this opportunity we have to just meet and study manifolds. Help us to understand what we're going over, and help students to ask good questions as they think of them, Lord. In your name I pray, Lord Jesus. Amen. All right, so we're still talking about tangent space. And in particular, I'll just remind you. So tangent space, right? So I still have a few more things to present about that. Just to recap, the big thing we learned last time is that the tangent space at P to M, right, is equal to the set of derivations which act on smooth functions on M, right? So the tangent space at a point to a manifold is the set of derivations which act on the manifold. And the big thing we proved last time was that for an n-dimensional manifold, the tangent space is isomorphic to Rn. All right? So one other minor point here I should get into. Lemma 3.11, he has the following. He has let this thing, iota, from the upper half space to Rn, denote the inclusion map. All right, very PC. And then for any A in the boundary of Hn, the differential of the inclusion map at A, which goes from the tangent space at A of Hn to the tangent space at A of Rn, is an isomorphism. And of course we're talking about isomorphism of real vector spaces. All right. So here's the deal. Let's run through the proof right quick with you guys. He's like, let A be in the the boundary of the half space, right? He says to show that suppose the differential of the inclusion map at A of V is equal to 0. All right. So then what are we doing? We'd like to show that that implies V equals to 0, right? If you can do that, then that will show that this is injective. And great. So he says, suppose, F mapping from upper half space to R smooth, right? And let F tilde be any extension of F to R, right? So here, F tilde restricted to upper half space is F, right? So it's a smooth extension of F to all of Rn. And those extensions exist by the extension lemma earlier in the chapter, early in the book, right? I guess that was in chapter 2. Anyway, so in particular, what's the relation between the function and its extension? Simply that F tilde composed with the Yoda map is equal to F, all right? And then, what do we have? Hence, if we look at V acting on F, all right, that's equal to V acting on F tilde composed with the Yoda map, which is, by definition, the differential of the Yoda map acting on V, acting on F tilde. All right. So V is where? So it's the same V up here, right? For V, an element of the tangent space at A of Hn, right? So it's a derivation. It acts on the smooth functions of the upper half space, right? So that's why VF makes sense. But VF is V of F tilde composed with Yoda, which then by the definition of the differential, which was what? I guess I probably should write that. We'll need that again today, right? Let's just remind ourselves how that goes. What's the definition of the differential? Remember how that went? If we have like any old function, smooth function from manifold M to a manifold N, then we said df v, right? And it acts on, let's say, G, right? Is equal to, what was it? V acting on what? G composed with big F, right? So that's the definition of the differential at a point. I guess I probably should slap some. You know what? I'm just going to live I'm going to live dangerously and not put the point on it. All right, you guys. Hope that's not pointless. Sorry, I'm an idiot. But you knew that already when you signed up for the course. So it's on you. All right, so basically, just pattern matching, right? Think of G as being the, Yoda as being the big F, right? F tilde is the G, matching the pattern, right? So that's why it's dA, and then the V is, well, the V. So I guess V is playing the same role. But that's definition of differential. All right, great. But then what? Well, this is equal to 0 because that was assumed. This is 0, right? So 0 acting on F tilde gives you 0, right? So, but F is arbitrary, right? Anyway, this implies then that the V is equal to 0, which then implies that the differential of the inclusion map is injective. All right. And then he says to show surjectivity, right? So to prove it's an isomorphism, we need what? We need that that mapping is linear, it's 1-to-1, and it's onto. It's linear because the differential is linear. We already know that. We just proved it's injective, right? By showing that the only thing which maps to 0 is 0. And to get surjective, or onto, you can let W be an element of the tangent space at A to Rn, arbitrary, and he says let V be in the tangent space at A of Hn by, define it by Vf is equal to W of F tilde, where f tilde is any smooth extension of f. And then he says, okay, so write W equal to Wi partial xi, summation over I implied. All right. Then Vf would be equal to Wi partial f tilde partial xi of A. All right. And then he says, this is independent of the choice of f tilde because the continuity of the derivatives of the extensions of f at A, f tilde A, are determined by those of f in the upper half space. And it's easy to check that V so defined is a derivation at A. So therefore the differential's injective. I wanted to just look at this proof, not so much because I want to belabor stuff at boundary points. In fact, I don't. I just want to at least do one calculation in here today that concerns like the boundary. Just to illustrate the method. The method is simply this, is like, to prove stuff about the boundary, you just look at extensions from like the half space to like the whole space, and essentially use the point that, like, if you look at that, the derivatives at the edge of things is defined, you know, by the extension. And that's all that's really going on here. So like I was telling you, you know, and what does all this mean? This means that even at the, so I think this technically was needed for the theorem I mentioned at the start of class, that the dimension of a smooth manifold with or without boundary, the dimension of the tangent space is n. It's isomorphic to Rn. This is part of that, because this is what establishes the isomorphism of the tangent space to Rn at like a boundary point. Because if we're at a boundary point in the manifold, we've got a boundary chart. And the boundary chart is a diffeomorphism of the point in the manifold to half space. Right? But the tangent space to half space is the whole space. It's Rn up to isomorphism. So anyway, I just wanted to share this short calculation with you guys, just to, you know, just to remind you, like, there's not much, like, I'm skipping over boundary stuff in here for the most part, because we just don't have enough time to do everything. But like what I'm skipping over is not that complicated. And essentially that picture in the book is super helpful. So like if this is a manifold with boundary, right? So you can kind of picture the tangent space, like the geometric tangent space like that. Essentially all that's going on is on the boundary. It's just like, if you can imagine it, it's just like that. That's the tangent space. It's just, basically you just let it hang over in some sense. That's all it is. It's not less of an R2. It's the whole R2. And so there's different ways we can understand tangent space. That's part of what I wanted to talk about today, is like different viewpoints for understanding the tangent space, right? I'm gonna do that later in the lecture, so let me not talk more about that at the moment. But just to say this, that to understand this, if you go to what's called the equivalence class of curves viewpoint of tangents, equivalence class of curves says that basically to understand a single tangent vector at that point, you can just think about all possible curves that go through the point that have the same vector like that. It's like every single one of these curves is identified with that tangent vector, right? So in short, well, anyway, let me shut up about that. My point is then, if you think about the boundary point, the same kind of thing happened. Like you can think about this curve, or that curve, or this curve, or that curve, or that, you know, all of these different things come in here to point like that. You can also think about, but then the more full story is, you can actually think about those curves kind of extending past the boundary. And you think about the extensions past the edge of the half space, and then those curves actually would extend pass through. And you can even kind of think about that and like transferring the curves that pass through the edge into all of Rn back through the, like something like that. It's always about extending past the half space, and like that's all of the proofs for the boundary stuff. It's always like a slight extension past the half space. All right, enough. So, moving along here, I wanted to talk about an important issue for a lot of examples, which is if we have oh man, that cost me 15 minutes. Dang it. I wanted that to be like 5 minutes. What happened? Oh, goodness gracious. Still no Jeff. Oh well. Sorry, Jeff. In the context of our manifold being what the Russians would call a linear manifold. What's a linear manifold? A linear manifold is simply a vector space. So if you have a vector space, there are certain identifications which can be made that, sort of like for a vector space, we can either view tangent vectors as derivations, or we have the choice of just viewing them as vectors. So in the context of a vector space, the tangent space can actually be identified with the manifold itself. But this is special to the problem of vector spaces. All right, so like let's make that discussion more explicit. And it starts with equation 3.5, which is just this. So this is let V be finite dimensional vector space, all right, and a point in V, all right, then define d sub V at A. All right, this is the directional derivative at A in the V direction. It is going to be a derivation on the smooth functions of the vector space, smooth real valued functions on the vector space. All right, and what's the definition of this? Same thing we did before. By, here it is, d sub V of A, it acts on F. How does it do it? It takes the time derivative, setting time equal to 0 after the differentiation is done, of what? Of F of A plus TV. All right. And the claim is this, is that we can define psi, all right, of V is equal to d sub V of A gives isomorphism. In other words, psi is going from where to where? Psi goes from, well, what is V? V is in V in this case, right? And what's the output? My claim is that this directional derivative at V, excuse me, at A in the V direction is a derivation. It's a derivation. So of course that would be the tangent space at A to the vector space V. All right. And this is essentially, well, it's part of proposition 3.13. Now 3.13 has a little bit more. It's got a picture, which maybe is helpful. And well, excuse me, I should say proposition 3.13 says more than just this. Yeah.
So are we going to take some vector space and then show it's isomorphic to a tangent space and find a manifold from that? Or
no, but I'll put this isomorphism into practice in an example in just a bit. What this is saying is that you have an identification of vectors in the space with derivations on the space. And like specifically, it would be something like this. Okay, Rn is a vector space, right? So what this specifically looks like in the context of Rn is just this. Psi is the map defined by its standard basis. Maps to partial, you know, we could say ui. Pick a point, yeah? So like at the point A, let's say, where partial derivatives with respect to ui are the usual Cartesian coordinates. Usual partial differentiation with respect to Cartesian coordinates followed by evaluation at A, right? Those are derivations on the smooth functions of Rn, and this is the isomorphism that's claimed. Remember, partial derivatives in Rn are at their base directional derivatives. They're directional derivatives in the coordinate directions. So this is not inconsistent what I'm saying. Now, proposition 3.13 says something a little bit more interesting, which I'd like to talk about. It says that if you've got two vector spaces, if you got a v and you got a w, and then over here you've got tangent space at A to V, and down here you got your tangent space at LA of W. And so, by the way, my usual notation LA, I would write L of A, but I'm just trying to hang with Lee here. And by the way, we're in John Lee's third chapter. We will continue to be in John Lee's book for some time, as I have chickened out of Jeffrey Lee's for the we'll eventually build up enough intellectual capital to get back to Jeffrey Lee's book, but we're not quite there yet. So this is L, all right? And he doesn't even have a name for it. He just writes this here, all right? He's saying you identify. I have given it a name. I just called it psi, all right? And if you're willing for psi to be multiply defined, it's the same identification down here, right? So anyway, so it's essentially the same idea. Technically, that would be a different psi, right? Psi. Anyway, so yeah, and then what goes here? What gets you from here to here? Well, that's the differential of L at A. And proposition 3.13 says that this diagram commutes. And I'd like to just calculate it, okay? So let's look at the calculation, which is the center of the proof. I won't do the whole proof. Oh, by the way, this isomorphism is not trivial. All right? Like, to actually prove this isomorphism, the details that I'm omitting are substantial. It's essentially the 40-minute thing we did last class. See, because what has to be done is you have to show that you can trade every vector for a corresponding derivation, right? And so the way that was done was that whole Taylor theorem argument, all of that. He references proposition 3.2 here. He says, just replicate proposition 3.2, proof of proposition 3.2. That's that big technical thing we did last time. But essentially the point is, because in a finite dimensional vector space, you can write any point in the finite dimensional vector space. Like A, we can write as, AI, EI, where, let me say VI for a second here. VI, where, V1, Vn basis, right? Maybe put an xi here instead. So any point you can expand in terms of coordinates in a basis. So essentially you've got what amounts to Cartesian coordinates in a vector space. So all of the arguments that we made can be made here as well. There are some fine print that's being omitted, but it's not that big an offense. Okay, so anyway, let me get to the point here. So this is a beautiful calculation. There's so much to understand here. I really love it. So the differential at A of L, differential L sub A acting on the directional derivative at the A direction at A in the V direction, that acts on F, all right? So to make sense of this, where is V, where is A? So A is an element of V, right? And where's V? So John Lee doesn't actually write these things in his textbook because he has enough sense not to clutter his paragraph with obvious things. But this is for A in V and for V in the tangent space to A of V, right? And where's F to make sense of this? F is a smooth function of real valued function on W, right? because the differential should move a tangent vector to v to a tangent vector to w, which then eats smooth functions on w, because it's a derivation on w. Anyway, so let's do it. So this is by definition, that definition over there, put on the first board, d dt at t equals to 0 of f of L sub, oh, I skipped the line, sorry guys. It's, my bad, I'm so sorry guys. D sub v of a, at a, of f composed with L. All right, so what does that mean? So the directional derivative of the composite of f with L, that in detail is d dt at 0, right? T equals 0 of what? Of f of L. Oh, I'm sorry guys, I keep losing track of what I was doing. F of L of what? Of a plus tv, right? That was the definition, right? We take f, the function we're differentiating, in this case f composed with L, and we evaluated it a plus tv. We differentiate with respect to t, we set t equals 0. Great. But L is linear. So what is this? Since L is linear, we can rewrite this as d dt t equal to 0 of f of LA plus t times LV. So if you look at, let's do some pattern matching here. What do we got? We've got this LA that's playing that role, right? And we've got this LV here, which is playing the role V does up here, right? So what is this? This is D in the LV direction at the point LA, acting on F, I think. Yeah, acting on F. Let's see here. So I think if I was more on top of things here, we probably could say something more about how this calculation relates to this picture over here. I said that this diagram commutes. What do I mean by that? I mean something like how to say this? Maybe that's the wrong thing to say. Maybe I'm not sure the diagram commutes there. That might not be right. Is it right? Let's see here. Here's a question. Is it true that DLA composed with psi, and let's call this psi v and let's call this psi w because they are different, right? So psi v, is that equal to question mark? No, so what is this I've just done? Let me draw some other. My apologies for this hideous Carolina blue. But this right here is this guy, right? And then how about the other path you could go there? What would it be? This way, right? We could go that way. So what would the formula be for that one? That one has the identification, the W identification going last, and L going first, right? So remember, the whole point of all of this is to generalize the notion of the derivative of a map, right? Like the differential is the generalization of the derivative. The derivative is the best linear approximation to a map, right? Best linear approximation to the change in the function. So if L is linear, it makes sense that the differential of L should essentially be L. So this is not a crazy thing to write down. Is that what we've shown here? Like, what is this? If I do dLA, you know, of psi v, what should I feed it? Maybe that's a big V. Let's let it have the vector v, right? What is that though? What was psi v of v is the, what is it? The directional derivative in the v direction at A, right? Hey, that's what we calculated, isn't it? See, because what this actually says is what? If you strip the f off this, what does it tell you? It tells you that dLA of dv at A is actually equal to what? This holds for all f, therefore it's an identity. It gives us the identity that the differential of L sub A acting on dv sub A is in fact the differential, the directional derivative at LA acting on LV. So this is equal to the directional derivative at in the LV direction at LA, right? Which is exactly psi W, right? Of what? Of L, right? Of V. Do you guys see that? So this is the directional derivative at LA in the LV direction. So the if I want to, I can say that that's psi W. You know, okay, to be more fussy, I really, this notation even falls flat a little bit, right? It's the identification of, because you can identify V with which tangent space? You see, that's the thing, is any tangent space to V can be identified with V. So to be fussier, this really should come with a little a up here, and this even should really come with like an L of A here, to be more honest. Now, John Lee is smarter than I am. He has the good sense to just use this symbol here and here to dodge all these pesky and uninteresting details, which I am spending precious class time on. But anyway, so look, we have this is equal to that. V is arbitrary. So this, right, is nothing more than dLA composed with psi acting on V. I'm going to drop the V if you guys don't mind. And over here, this is psi composed with L acting on V. I mean, technically it's the dressed up size, right? But the point is, this holds for arbitrary V, therefore, yes, indeed, the diagram commutes. All right, so anyway, a lot of this just to say we have a canonical isomorphism, a basis-independent isomorphism of a vector space and the derivations of the smooth functions on the vector space, and it's just given by directional derivatives. This is the isomorphism. What does that actually look like in practice in terms of calculation? So here's an example. Example one, I suppose. If I had something like, you know, f of A equals to, you know, oh goodness, I don't know. Let's say something really boring, like A1, 1 plus A 1, 3, comma A2, 2 plus A, you know, 4, 4 there. And let's suppose F is actually a mapping from our 4x4 matrices to R2. Oh yeah, thank you. Just to give you a kind of a random example of this stuff. Here, is that a linear map? I mean, yeah, that's a linear map. You can check if you have A plus B. It's linear. Okay, so if we were to calculate, let's say, the differential at f at the point A, and let's let it map, like partial x11 at the point A, how would that go? Right. So I'm pointing out, guys, that like an arbitrary A could be written like this, like x I j e I j. I guess I should write a I j. Well, anyway, my point is that x I j of A is equal to. Oh, my apologies. I guess I've already put the subscripts down over here, so I'm stuck with it. It's not great. Maybe I should put all my maybe I should put all my indices up to make this example less, convention violating. Okay, so then how does this work? Well, what should I do? What's the definition? I'm supposed to let this do what? If I follow the definition, I'm supposed to let this hit like G, right? And how does that work? It's supposed to be partial x11 at the point A, and it acts on what? G composed with F, right? Is that right? Yes. All right, so just to get it over with here, what we're looking at then is G of f of x, using big X as like a matrix variable here, okay? And that it gets evaluated A at the after that's done. All right, so that is actually partial x11 evaluated A of what's G of f of x? Well, in terms of variable x, you're looking at x11. I'm sorry. My bad. I put the indices up. So x11 plus x13, comma x22 plus x44. All right. That's the formula for G composed with F here. And then you know how to do these partial derivatives, right? That's what? 1 plus 0, comma 0 plus 0, right? Which is just 1, comma 0. My bad. I was trying to not use the identification to start with, but I have done it inadvertently. See, because, well, that's the thing. Oy, oy, oy. All right, let me fix this. To be fussy, I'm supposed to have, so what I should have written there to be more technically, good grief. All right, what's the problem? The problem is, oh.
Sorry, I'm saying something not right here. Let me backtrack a bit. This is not, there's something kind of right about this, but it's not what I wanted to write. Sorry, guys. This is all Jeff's fault. Thanks a lot, Jeff. All right, so
Safe to blame him.
okay, so what I was supposed to do, all right, let me try this again. All right, so this is supposed to be equal to, like, so let's say that over here in R2 we have coordinate, so I've used basically x11, x12, x44 for my 16 coordinates in the domain. But in the range, I'm just going to call these guys like y1 and y2. Okay, there's my coordinates over there. So if this is the push forward from R4 by 4 to R2 with those coordinates, that means that this should be a linear combination of the derivations with respect to y1 and y2. In other words, you should be looking at like dfa partial x11 at a acting on what? Acting on y1. Partial y1, all right? Plus, same song and dance, but with acting on y2. Partial y2. And sadly, I'm getting ahead of myself lecture-wise. These are supposed to be at the appropriate point, which I will call f of a. All right. So how does that work? Now this actually is what I should have been doing. So that's literally partial x11 of y1 composed with f, right, of x, of the matrix variable x at a, partial y1 at f of a, plus partial x11 at a of y2 composed with f. If I was smarter, I would have given myself something that was real valued so we wouldn't have run into this, you know? But I did what I did, so here we are. And then you got your partial y2 at f of a. All right. Now, let me save myself a little bit of writing by doing some color-coded calculation right under my thing. Like this is what? This is just x11 plus x13, all right? And this guy right here is x22 plus x44, all right? And so when I take the derivatives, I just get what? 1 plus 0, right? Partial y1 at f of a plus what? 0 plus 0 partial y2 at f of a, right? In short, the answer is partial y1 at f of a. That's the push forward of this. All right, what does that have to do with this canonical isomorphism I'm just talking about? The canonical isomorphism I'm just talking about says that you can write this is equal to, 1, 0. That's equal to 1, 0. So you can do like that. And let's see here. And if you were to just differentiate this with respect to like partial x11, you would just get 1, 0. Not an accident. So John Lee does a pretty good job on that page following this proposition of explaining that with these identifications made, the differential or the push forward at a point just becomes the Jacobian matrix times the vector.
So like that's the by design. This is all intending to generalize the Jacobian matrix construction of advanced calculus. So, all right, let me go on here. Does this help? I mean, I don't. Yeah. Let me restate that. That helps. There. I have defined it to help. All right, so moving along here. I should mention there's a lovely proposition which you guys get to prove in your homework, right? And that is proposition 3.14. And what's it tell us? I'm mostly talking about this because I think I need to talk about the notation so you guys know what it means. But this proposition, whatever. Proposition 3.14 concerns a product manifold. So if you have, M1, M2, MK smooth manifolds, all right? Then you can define pi j, a mapping from the Cartesian product of all these guys, all right, in the obvious way, like pi j of, let's say p1 dot p k is just equal to what? It's equal to? You guys tell me. pj, you got it. Excellent. So here's the deal. The map alpha, which goes from the tangent space at P to this product manifold, M1 cross dot dot cross MK, is mapping to the direct. So this is the thing I wanted to talk to you guys about. Direct sum, P1, M1, plus circle, dot, 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 plus circle, T, P, K, M, K. Do you guys know what that means? So what that is the external direct sum. So this right here is the external direct sum. It's a way of building a new vector space from an old. All right? So in the external direct sum, everything has the form. There's an isomorphism between. Well, anyway, in the external direct sum, everything can be written as a linear combination of vectors from each one of the things being summed, and that is unique. All right. So the notation is kind of onerous right here. Let me switch to an easier notation. If I had like vector space V1 direct sum vector space, like k of them, that is isomorphic to the Cartesian product of V1 through Vk. And the isomorphism is simply the following. The isomorphism, in some sense, you could really think of this as being the Cartesian product of the vector spaces. That's not entirely wrong. But the isomorphism here is just this. If I have, let's say, V1 plus V2 plus da 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 plus Vk, that is interchangeable with V1 comma V2 comma da 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 Vk, right? And that's an isomorphism. All right, anyway, I can tell you more about it in office hours if you want to know more, but it's an external direct sum. All right. So what that means, among other things, is in the external direct sum,
these subspaces are independent. So like there's no intersection except at 0 of the tangent space to this one and the tangent space to that one. All right? So they're independent subspaces as they appear in the tangent space of the whole thing. But this defined as, so how's that defined? Alpha of v is, all right, so here's it goes. D of pi 1 at p acting on v, d of pi k at p acting on v, right? That is, so the statement is that that is an isomorphism. All right. And then he says, the same is true if one of the spaces M sub I is a smooth manifold with boundary. So when I was first carelessly reading John Lee's chapter 3, that weirded me out. Wait a minute, why can just one of the M's be a smooth manifold with boundary? But remember, if we have 2 of them, we get a corner point. So just one of the M's can be a boundary. All right. Now, all right, here we go, finally. Yay! I've got to the part that I was itching to do with you guys. So let us talk about computations. Actually, are we good on this? Oh, I'd like to erase this actually, because I don't think I'm really going to use it, and it's kind of taking up a lot of real estate that's not particularly interesting. Though, I mean, I think this is a great thing for you guys. Let's get a homework problem. I don't think it's that hard of a homework problem. I think it's mostly just battling notation. A lot of your homework's like that this week though, right? So, except for that chain rule problem, if you take the wrong approach. But the thing is, Ernesto, we could take the composite with curves. That is actually contained in the chapter. We could use that for that homework problem. Because at the end of chapter 3, he introduces how to view the differential in terms of velocity vectors. So we should get to that today, hopefully. In the interest of that, let me go on. So, because you really like to do that homework problem that way, as opposed to the way I showed you. Whoa, right? Yeah. All right, so let me entitle this calculations. All right, calculations. So let's suppose we've got a manifold, and you got a point, all right? And at that point, you can talk about a vector v, right? And let us suppose that this is all happening in the context of a coordinate chart, u, all right? And, all right, so fine. U, right? And maybe there's another coordinate chart also at this point, right? There could be 2. We'll call that u bar. All right. And all right, so first of all, if v is an element of the tangent space to p at M, I would like to prove to you that, let's see, there's a bunch of things I need to prove, so let me just try to, I'm just going to try to do, I'm going to regret, whatever order I do things in, guys, here, I'm going to regret it, but let me just start doing things, and once the dust settles, we'll see if I proved everything we need to prove or not. So down here, you got your, let's say, x of u. All right, John Lee would call that phi or psi or something, right? Great. And then over here, you got your x bar, right? So that takes us down to another copy of Rn, and here's our x bar of u bar, right? Okay, so one of the things I'd like to prove to you is that, so let me just state it as a theorem. So here's one of the theorems we need to know and use, which is that TPM is the span of partial xi at p, I equals to 1 to n. And if v is an element of TPM, then v is equal to vi partial xi at p, where v upper I is given to you by v acting on the ith coordinate function. Now, the context of this theorem is my picture. x1 through xn furnishes a coordinate chart at p for us. All right? Are we good? Let me prove this theorem. I'm not going to prove all of it. We've actually done a lot of the heavy lifting already. The most heavy lifting is to prove that partial x, well, that's, okay, medium lift. First of all, proof, I'm not going to belabor this today, but I bet you guys could prove that partial xi at p is in fact a derivation, right? I think that was a homework problem you guys had, maybe. Or at least we've done it in a previous day. If not, I'll put it on your test. So you can prove that that is linear in Leibniz, all right? Point number one. Point number two, we know, what else do we know? The dimension of TPM as a real vector space is n. We proved that last time, right? My claim is that, what is this claim? This claim, I didn't quite say it right. I should say, and you know, to be clear, these things, right? Is basis. Where, there, that's better. So my claim is that the coordinate derivations give us a basis to the tangent space. All right? There's n of them, right? In order to be sure they're a basis, what do I need to do? There are two ways we can go here. It's a finite dimensional vector space. You've got n vectors. If you show that the span is onto, you're done. Or what's easier, you could show that these are linearly independent vectors. Let's do that. How do we prove that this basis is linearly independent? Let us do that carefully. So suppose that the sum I equals 1 to n of ci partial xi at p is equal to 0, right? I actually just got to the good part, so your timing is good. I wish I was joking, but I actually really like everything we're doing pretty much here on out a lot more. So, yeah. So we are in the midst of proving that the partial derivatives to the basis with respect to the coordinates are in fact a basis. Okay, so we suppose that that linear combination is 0. My goal is to show that all the coefficients are 0, right? That would prove linear independence. What should I do? How about this? Act on x upper j. This is in fact a what? This is a smooth function from u to r, right? And by our extension theorem, there exists a smooth extension of this coordinate function to all of m with the smooth bump function magic. So we can regard the jth coordinate function as if it's a smooth function of all of our m, therefore we can, anyway, we had this talk before. We can look at functions which are only defined locally, right? So fine. So act on that. What you got? Sum I equals 1 to n of ci partial xj partial xi equal to the 0 derivation acting on xj. How's that work out? That's 0, right? But what is this? A homework problem I should have assigned you if I didn't is to work that out. And if you work that out, you will get the Kronecker delta. Kronecker delta ij, right?